Okay, good morning, everyone. Welcome to class today. Hopefully, as you recall from Dr. Green's announcement, today we'll be talking about magnetic field-assisted finishing. A couple of new unfamiliar faces here. If you don't know me, I'm Dane Ungerite. I'm your TA for the class. I'll be covering for Dr. Green's while she's in Paris. She'll be back on Monday for the lecture. Before I get into today's material, I just want to make a couple of quick announcements related to the class. Homework 1 has been graded. The plan is for those grades to be released as soon as I finish the lecture today. So after we finish the lecture today, I want to go back up the hill and go ahead and release those grades. If memory serves me correct, the average was about an 85 on that homework, so a little bit lower than we were hoping for. And just overall course policies. So you have 1 week to appeal your grades if you think that the assignment was graded unfairly, or if you think that points were taken off when they shouldn't have been. You have 1 week from the moment that the grades are released. So today's Friday the 20th, or the 21st rather, so you have until Friday the 28th to contact Dr. Greenslet to dispute any sort of grade that you may have received for that assignment. Quick reminder on how the homeworks are graded. Half of the grade is just purely based off of completion, so that's whether or not you put an answer for every single question. If there's just one single question or one part of a question that you did not attempt to answer, you don't get any credit for the completion, so it's all or nothing. And then we'll randomly select 1 or 2 questions, and then we'll grade that for accuracy based off of the rubric that's given to me. Don't try and dispute the way that it is graded. That is well defined in the syllabus, and you're kind of already aware of that. So if your issue is with that sort of grading scheme, I think it's unlikely that you'll be successful in your appeal. But if there's anything specifically like you're taking points off for an answer that you felt like should have been correct or deemed deserving of credit, feel free to reach out to Dr. Greenslet. My recommendation is the best time to do that would be during her office hours. So she'll be back on Monday. So my recommendation is over the weekend, look at your homework. If you're fine with your grade and you think it was graded fairly, then no action needed. If you do have any disputes, stop by her office hours on Monday. I can also talk to you about the homework solutions and how it was graded in my office hours on Tuesday or Thursday of next week. But technically, grade changes have to be approved by Dr. Greenslet, so not just me. Okay? All right, so that covers all I really wanted to announce. Also, I guess for a quick reminder, your exam's coming up in a little less than 2 weeks from now, so now's a good time to start reviewing for that. And then homework 3 is due next Wednesday, this upcoming Wednesday, and then your next project assignment, I believe, should be due the following Wednesday for your introduction and figures. All right, I think that's all I have to say for announcements. So let's get started with the material. So today we're going to be talking about magnetic abrasive finishing, or MAF. It is sort of the bread and butter of Dr. Green's lab, which I'm a part of. So she's a certified expert in this technology. So and I don't directly deal with MAF myself in my own research, but I have plenty of colleagues who do, and I've sat in on many of their presentations, so I'm pretty knowledgeable, I consider myself at least, in this field as well. So let's talk about what is MAF first. So magnetic abrasive finishing uses magnetic particles mixed with an abrasive to grind away and abrade and finish a workpiece. So there's 2 sort of setups that you can use for it, demonstrated here on the left and the right. So on the left here, we have a ferromagnetic, the case for when your workpiece is ferromagnetic, and on the right, this is the case when your workpiece is not ferromagnetic. So your workpiece does not have to be ferromagnetic for this process to work. So here we have a magnet with the north and south pole. Your workpiece here, which is ferromagnetic, serving in this case as a north pole. So your field lines are going to be connecting from your workpiece to your magnet, and then you have some larger magnetic particles mixed with a finer abrasive. And what's going to happen is those magnetic particles are going to want to align with the magnetic field between your magnet and your workpiece. So they're going to sort of form like a brush almost. And then your abrasive is going to be pushed by that brush along your surface. So your magnetic particles are going to, as you move your magnet from side to side, your magnetic particles are going to follow that along with the magnetic field, and they're going to push into and slide along the workpiece, your abrasives. So that's going to grind away and gradually remove these burrs. So you can see here, this is your unfinished part, and this is the part where it's already passed through and you've already gotten a smoother surface. So that's the case for a ferromagnetic workpiece. Now what happens if your workpiece is not ferromagnetic? You can use one of these two setups you see over here. So on the left, you can just simply rest your workpiece on a magnetic table, in which case it behaves the same as the previous case. Because if you just essentially treat your workpiece and your magnetic table as one sort of piece, your field lines are going to connect, they're going to permeate through your workpiece and go through the table, and then it's the same process. You're going to have your particles aligned with the field lines, and it's going to brush and move along your abrasives along your workpiece and polish your surface. Another thing that you could do is you could just simply use a single magnet like this, and then your abrasives will still be attracted to your magnet, because your abrasives, not your abrasive, your magnetic particles are still going to be attracted to your magnet. Your field just won't be as strong. So you don't necessarily have to have a ferromagnetic table, but this will weaken your magnetic flux a little bit. Oh, another important point I should mention is that we're talking about magnetic particles and abrasive separately. You can use a ferromagnetic abrasive. So if an iron particle is strong enough, depending on what your workpiece is and how hard your workpiece is, if you can use a ferromagnetic abrasive, you can just make your brush be the abrasive itself. And you can just manipulate your magnetic abrasives using your magnets. So it doesn't have to be two separate mixtures. It can be just one simple ferromagnetic abrasive that you move along. We don't talk about a lot of math in this course, but just conceptually and to sort of drive this home, the key parameter for MAF is your magnetic force. So the force that's exerted on your magnetic particles is illustrated by this equation here. So you have your force equal to your volume, which is the volume of your magnetic particles. So this entire mass of your magnetic particles. So that volume multiplied by the magnetic susceptibility of those particles. Magnetic susceptibility is a material property of your particles. H represents your magnetic field intensity. It's measured in Tesla. Hopefully you recall that from your introductory physics level course. So H is a property of the strength of your magnetic field and how strong your magnets are. And then you also multiply that by the gradient of H. The gradient, hopefully you guys are graduate level engineers at this point. So gradient is a spatial derivative. It is a vector quantity, which makes sense given that this is a vector and force is also a vector. So you take the gradient of your magnetic field intensity, so your rate of change through space of your magnetic field intensity, that will influence your magnetic force. Okay, so now that I've given you a brief little overview of the process, let me illustrate this in a more fun way with cartoons. All right, so volume should be off for this, which is good. So how many of you guys like Tom and Jerry in here? Good, lots of you. All right. So in this case, you have a magnet and you have an iron. Your iron is ferromagnetic, right? In this case, Tom wants to get this cat to move using that magnet. Cats aren't magnetic though. So what do? Don't try this at home. You introduce a ferromagnetic particle, or in this case, an iron. So the analogy to MAF is the cat in this case, the orange cat, is your abrasive, right? Let's skip ahead a little further. Here we go. So in order to move your abrasive, which may or may not be ferromagnetic, if you introduce the ferromagnetic element, in this case, your clothing iron, you can manipulate your abrasive. Let's skip that. Make it move around. Another important characteristic of MAF, or I should say characteristic, but a key advantage of it is you notice that Tom, the other cat manipulating the magnet, isn't in the same room. It's permeating through that wall. That wall is not ferromagnetic. And however he moves that magnet on the other side, the cat's going to follow that movement. So just looking at that intrinsically, what does that do for your actual finishing operations? So if you have some sort of complex internal geometry that's hard to get to, you don't have to actually insert your magnet and your tools inside of your complex geometry. You can manipulate from the outside. So it makes it very useful for internal finishing operations. OK, let's get back to a little bit more serious here. Let's go full screen. Oh, I don't want that to play yet. Let me pause these for now. OK. So overall processing mechanism, so you have the magnetic force, which I gave you the equation on the previous slide. That's going to be the equivalent of your cutting force from your traditional manufacturing processes. So how far, like how strong is your abrasive being pushed into your workpiece? So you have two elements. You have your magnetic force, which is being provided by your magnets, and then you have a dynamic motion of your particle. So by moving that magnet, that's where you get that relative motion and that abrasion. So those two together, those provide your depth of cut and your length of cut. So the depth of cut is primarily influenced by the strength of your magnetic force. So if you pull harder on your abrasives, you're going to have a deeper cut. If you have a weaker force, you're going to have a much smaller depth of cut. So you can try and optimize your parameters based on how much material removal you want. And then the motion and the path will affect what sort of length of your cut, what sort of path is your machining process going to follow. So that together gives you a material removal rate. It also will affect your surface roughness. How rough is your surface? Obviously, a larger depth of cut could result in a worse surface roughness. It also affects the lay and the integrity of your surface. So now I'm going to show you two different videos of MAF processes, one successful, one unsuccessful. So first, we're going to start with the successful process. So over here, we have two permanent magnets here. So on the bottom and on the right side of your cylindrical workpiece. And now what's going to happen is, in this process, we're going to rotate our workpiece. It's in a chuck on a lathe right now. So we're going to rotate our workpiece. And what we want is we want our ferromagnetic particles and our abrasive. So we have a mixture of solid particles here. So we have iron particles mixed with an abrasive. And we're going to want these particles to be pushed up against this surface, this curved surface of our workpiece. Our magnetic field lines should follow as such. And so we're going to rotate our workpiece, and we want these particles to stay in place while our workpiece rubs against those particles, smoothing out the surface. And because I said it's going to be successful, that's exactly what's going to happen. So it's going to get up to speed, and you'll notice that your particles are staying in the same region. They're not jumping around and flying around inside of that tube while it's rotating. So that's a generally successful. You'll have a couple maybe that scatter out, but for the most part, they're staying in contact with the workpiece. So that's what the process should look like. All right, now I'll show you a case of an unsuccessful polish. Now, see, it started off sort of stationary, but as it really gets up to speed, you'll see your abrasives going all over the place, everywhere. So you're not really getting that relative motion between your between your particles and your workpiece surface. So you're not really getting any machining work done. Now let's talk a little bit about why is this the case. So the main reason why the one process was successful and the other wasn't was a matter of the strength of your magnetic force. So there's two sort of forces, there's two primary forces at play. You have your magnetic force, which is sort of a normal force being pulled into your workpiece. You have your normal force that should be equal and opposite to that force. And then you have friction, right? So as your workpiece is moving around, there's going to be a frictional force between your abrasives and your ferromagnetic particles and the workpiece surface. If your magnetic force isn't strong enough to sort of withstand that friction, your particles are going to go flying off. Whereas if your magnetic force is strong enough, that friction force is going to keep it in place. So it's a matter of how strong is your magnetic field is to keep them in place versus the friction of the workpiece motion. So that's something to keep in mind when you're designing this process. You have to make sure that your particles stay in place. Okay. There should be a picture here. There we go. All right, so let's talk a little bit about some of the advantages and the outcomes that you can get with MAF. So the first advantage is what I sort of demonstrated to you already with the Tom and Jerry video. So you have an unimpeded flow of magnetic flux through your workpiece, assuming that your workpiece is not ferromagnetic. If your workpiece is ferromagnetic, your flux will permeate through your workpiece, not, well, let's see here. How do I just, it's probably better to show you on a later slide for that. But your magnetic field lines will go like into your workpiece and follow along the length of your workpiece if it's ferromagnetic. If it's not ferromagnetic, it should just go and pass straight through it and be unaffected by your workpiece. So that allows you to, like I said before, you can sort of keep your tooling external to your workpiece and not have to go inside and allow it to reach those internal features more easily. Another advantage is that your magnetic abrasive and your abrasives are flexible chains that can conform to your workpiece surface. So you have a mixture of powder, and that powder can conform easily to your workpiece surfaces, so you can finish complex internal geometries. So those two together allow you to finish and reach areas that are hard to reach with conventional tools. Some potential outcomes that you can achieve with this process, if you do a good enough job on the MAF, you can create hydrophilic and hydrophobic surfaces if you can get a fine enough surface. So that's an interesting property. They're not super strong in hydrophobicity or hydrophilicity relative to like laser machining finishing and other various processes, but you can get a hydrophilic and hydrophobic response using an MAF process. So that just sort of shows you how good of a surface you can get. Low wear and low friction parts you can produce with this, again, because of that nice surface finish. Depending on how you finish the part, you can get some adhesion control. You can control reflectivity if you want to try and get a reflective surface with that. You can also get a finer control of your surface area per unit volume. Obviously, if you have a rough surface, you have a high surface area relative to your volume versus a smooth surface where you have a lower surface area. Over here on the right side, we have a picture of a stent. A stent is a device that is used for treating of blood clots. So what will happen is a doctor will insert the stent into an artery and then expand it with using a balloon, which you can see in this diagram here. This little clear plastic part is a balloon that's inside the stent. So you'll inflate it and it'll expand out, and it'll expand your blood vessel and allow whatever clot or was clogging up that artery to pass on and become unblocked. But these stents are made out of metal, and you can see there's a relatively complex geometry, so they're often made using like a laser process that results in many burrs in this. So these parts need to be finished and polished before you can actually use them, because if your stent is sharp, you're going to be cutting up the person as you insert it into their artery. So they have to be a nice smooth surface. So one area of research that we've done in the lab is trying to use MAF to polish these stents, because they'll conform to this surface and they don't use any sort of harsh chemicals. All right, here's a picture before and after polishing using MAF. So on the left side versus the right side. On the right side, you should hopefully see that it's much shinier. We have some assay values to quantitatively show you the impact that MAF has had on the surface. So on the external surface of your stent, the original surface was 0.2 to 0.4 microns, or 200 to 400 nanos SA. And they were able to polish it down to about 10% of what it was before. So now from 200 to 20 microns, 20 to 70 microns, not microns, 20 to 70 nano. And then on the internal surface, we were also able to get a very good surface finish between it started off initially 0.4 to 1.4 microns, and now we're 0.02 to 0.2 microns. So it's very effective for this magnesium alloy stent. Okay. Now we're going to talk a little bit about magnetic tools. I think for today's lecture, I think I'm only really going to have time to focus on this first one here. So we sort of have three classes of these magnetic tools. So we have a mixed type magnetic abrasive. MRF stands for magnetorheological fluid. And then we have MF-based slurry. And the primary difference for you guys to understand what's the difference between these slurries is primarily the particle size, and as a result of the particle size, also your magnetic force. Because if you have a larger particle size, you have a larger magnetic force generally, because like I showed you with the equation, your magnetic force is directly proportional to the volume of your magnetic particle. So from left to right, we have larger abrasive and they get progressively smaller and smaller. Your MRF-based fluids are usually micron-level magnetic particles, and your MF-based slurries are usually nanoscale. So you can get much finer surfaces, smaller material removal as a result, but finer surfaces and a better surface finish with the ones on the right versus the ones on the left, which are more aggressive. Okay, so here we have a picture of one example of MAF, and there's multiple different ways in which you can achieve MAF. So we're going to start off talking about with some static magnetic field applications. So in this case, we have two magnets, a north pole and a south pole. And then over here we have we can call it a ferromagnetic abrasive or a mixture of ferromagnetic particles with an abrasive. And then the cylindrical rod is our workpiece. And what we're going to do is we want to polish and finish the outside surface of this rod. The way we're going to do this is we're going to simultaneously rotate that rod. So we're going to get relative motion along the curvature of the surface. And if we want to polish the entire length of that workpiece, we can also feed it back and forth. So we're rotating it and we're moving it back and forth. So we're polishing the entire outside surface. Your magnetic field is going to keep your abrasives inside of that field right there. They're going to align there. So as you're moving your workpiece through that field, your abrasives should stay inside that field and they're going to rub against your workpiece. Over here on the right, we have examples of workpieces that were polished using this exact setup. We have pictures before and after the polishing, and you can see they're much shinier after polishing than versus before. Yeah, in this case, these were silicon nitride rods. So they were not, this is a case of a non-ferromagnetic workpiece. Okay, I should have pulled this up before class, forgot to. All right, so here's another example of an application using this same setup. I don't want to use edge. All right, so this is a research paper. I highly encourage you guys to read this at home. It's only a 4-page article, so you can read this one really quickly. What do you mean access to? I'm on UF Wi-Fi. Ugh. Can I at least look at the pictures? Oh, there we go. Okay, perfect. So, should I go through the abstract real quick? Sure, we'll start off. All right, so this article is basically describing an application using MAF to finish drill bits. So these drill bits are made of high-speed steel, which, as you should hopefully be aware, are is a very hard tool steel. So they're very difficult to polish. And then, if you're familiar with the geometry of it, you have that sort of helical cut in your part. So they're very hard. They're a relatively complex geometry that aren't the easiest to finish and smooth out and deburr. So this process uses magneto-abrasive machining, which is just another form of MAF, to accomplish this. Let's see if I can get that picture here. Here we go. So here we have a magnetic abrasive powder here. You can't see, the magnets aren't shown in this picture, but they're being held basically in place through this magnetic field. And then we're moving this drill in and out of your abrasive and finishing that part. Again, I don't want to go too into detail with this part. It's a 4-page article. You can read it pretty quickly. So it will let me view the PDF now all of a sudden. But yeah, as you can see, very short article. Highly encourage you to read this. Won't take you very long. I'll pause here for a second just for people watching on video who may want to grab the title and the author real quick. All right. So that's just another example of an application using MAF. Let's talk about another way you can do MAF. So this is again using a static magnetic field. So this time we're going to rotate our magnets for this new setup. So over here we have just our table, which is ferromagnetic in this case, and then we have a non-ferromagnetic workpiece. You can see it's got a rather funky geometry to it. And then we have a tool post with a magnet embedded in it. So we have magnetic field lines demonstrated with these little dashed lines here. and then you have a mixture of magnetic and abrasive particles over here. So what's going to happen is, like I said before, your magnetic particles are going to align with your field lines and sort of film these long chains like a brush, like a long strand of magnetic particles. And your abrasive will be resting on the bottom of your surface. And then you're going to rotate your workpiece. And those chains that are on your magnet are going to rotate with it. And it's going to sort of brush your workpiece and move that abrasive and finish it and grind it away. Here's an application using this technique. This is a titanium alloy airfoil. So once again, you have a rather complex curved surface being finished using MAF. Also, titanium is a fairly hard material too. Another issue that you often worry about with machining titanium is the heat transfer properties. It's not a very thermally conductive material, so you have these sort of concentrated spots of heat. I'm not going to say that this process generates no heat, because you do have friction, but it's not. I don't think it's an excessive amount of heat, so you're still able to machine titanium with this process. All right, here we have an example of a bent polishing. Do we have any members here of Pi Tau Sigma in the lecture? No? It's an engineering honor society. I think specifically mechanical engineering honor society. No? No Pi Tau Sigma members? Tau Beta Pi, anyone? I'm the only Tau Beta Pi guy in here? Okay. So if you want to ask me what a bent is, it's basically this guy here. It's just a little emblem, it looks like a giant necklace almost. So this is just their crest basically right there. So you have a picture of what the bent looked like before. You can see it's rather dull and grayed out. It's a very rough surface. There's two ways that traditionally you'd polish it by hand, as you can see here. So here you have just a cloth with an abrasive, and then you're just hand polishing and grinding it away. That's typically it would be very tedious, obviously. But you can also use MAF instead to polish this guy. So here we have a picture of the setup. I'll play the video for in a second. So this is, again, using that same setup that I described on the previous slide. So you have a rotating magnet. The gray parts that you can see there, that's your magnetic brush, essentially. So those are your magnetic particles. And then that white liquid that you're seeing there, that is your abrasive fluid. So that is an abrasive that we're basically brushing with this magnetic brush with that rotating magnet, and we're abrading away and smoothing out that surface. That's a much longer video than I thought. So when it's all said and done, you get the end result you see on the right here. So comparing left to right, you can see it's much brighter, much cleaner looking. It's a much smoother surface. And again, this is a rather intricate geometry, so you have dents, you have some tight corners in there, and you're still able to relatively match that form. So you haven't compromised the shape. You can still clearly read Pi Tau Sigma, even though it's a relatively complex geometry. Whereas if you're doing it by hand, trying to get into that little gap between the two legs of your pi there, well, I didn't mean to do that, but that worked out great actually. So trying to get that by hand would be incredibly difficult. Whereas with MAF, it's a lot easier. Here's another example using essentially the same process. So this is a prosthetic knee implant here. You can see it's a curved and rather complex geometry. So in this case, we're going to have still that rotating brush, but we're going to use a robot arm to move our knee implant. So we have a mostly non-magnetic jig that's holding and clamping down this knee, and then we have if you look really closely over here, this little plate here, this part of the holder is magnetic. It's made out of carbon steel, and that's going to allow our field lines to go from our magnet to that carbon steel plate. And then here we can see the polishing in action. You see the abrasive. Oh, that was a short video. I'll play it again. So you have a rotating brush, essentially, of magnetic particles, and then you have a abrasive paste on your knee that you're moving along, and you're brushing away and you're abrading your material. One analogy that a colleague of mine likes to use for this is that it's kind of like brushing your teeth. Your magnetic particles are your toothbrush. You have your magnet on the base, and then they're creating these strands of ferromagnetic particles that are your toothbrush-like fibers. And then your abrasive, that's your toothpaste. And you're using that to grind you don't really grind your teeth when you brush your teeth, so that's where the analogy sort of falls apart. But you're still sort of have that same brushing motion instead of actually trying to and you are cleaning it, but instead of grinding away, you're grinding away plaque, you can look at it that way. So it's very similar to brushing your teeth in that way. All right, here's some quantitative results of the knee prosthesis polishing. So on the left, that's sort of a traditional result that you would get just by traditional buffing, what's used commercially using traditional methods. And then on the right, you can see much smoother surface profiles that we were able to achieve using MAF. So again, typically they were getting 2.4 to 8.0 nano. Now we're getting 2.2 to 4.9 nano. So a little bit better than the traditional methods. And again, once again, a very complex geometry. Okay, let's talk about another different way that you can do this. So it's very similar to what we started off with the class, but now we're using 4 magnets. So we have north-north, south-south. So your field lines are going to be going from this north to this south, and then again from this north to this south. So you have sort of 2 curved bends. So you have 2 sort of regions where your magnetic abrasives are going to be concentrated. And then once again, you can either rotate your magnets or you can rotate your workpiece, either or. In this case, I think this diagram is specifically showing you're rotating your poles. You can also vibrate or move back and forth along the axis of your workpiece, your poles, to move your abrasives along with your magnets. Okay. Dr. Greensley originally told you guys to look at page 51 of your textbook, which I'm still going to encourage that you do so when you get home today. But I've gone ahead and pasted the pictures from your textbook into this slide so you can see exactly what the figures we're going to talk about today. Still, go home and read that section of your textbook. This is a good example of a good section on what happens for ferromagnetic versus non-ferromagnetic workpieces. Because, like I said before, you can polish both ferromagnetic and non-ferromagnetic workpieces, but they do work a little differently. So at the top, we have an example of a non-magnetic workpiece. So you have a north pole, you have a south pole, and then, like I said before, you have your field lines that are connecting your north to your south pole. And as a result, your magnetic particles and or your abrasives will be pulled up into this little region of your tube. I didn't even touch it that time, I thought. Okay. So again, we're going to rotate and or vibrate that workpiece, same as we talked about before. Now let's talk about what happens when you have a magnetic workpieces. Your field lines are going to work a little differently. Because your part is ferromagnetic, or just magnetic in general, your field lines are going to want to flow through your workpiece. So as you can see here, the field lines go all the way around and flow through your workpiece. They don't pass through it. They go into your workpiece. So that works a little bit differently. As a result, that will often weaken your magnetic field to a smaller region. So it's not exactly demonstrated very well, but you'll have fewer particles. So it'll still work. You're going to be connected to your abrasive are going to be attracted to this region here because they're going to want to flow. Like I said before, your magnetic particles are going to want to align with your field lines. So they're going to want to try to align with the inside of that workpiece. They won't be able to perfectly align with it because obviously they can't permeate into your workpiece. But they will still be attracted and they'll try their best to align with your workpiece. So it'll still work, but you might need a stronger magnet. Okay, now let's talk about a specific application and contrast. Let's contrast it to a tradition. I guess it's a non-traditional method, but MAF might be a little bit advantageous for this application. So flexible tubes and specifically catheter shafts. So catheters are tubes that you use to basically introduce fluids into the body. They're often used, like if you ever had an IV before, you'll use a catheter to like introduce fluids into the body. But as a result of it's kind of like the stent, you need your catheter shafts to be very flexible. So in order to do this, you machine these super tiny slits into the metal, which you can see in these diagrams here. So we have here and you have here. Because these slits are so small, they need to be laser machined. The reason why you have these little tiny slits into it is to, like I said before, to make it sort of bend. So if you have like a slit in here, you have a gap in material, it's going to allow it to bend further. So you laser machine these slits, and as a result, it makes it more flexible. But the result of laser machining is you get these burrs because you're melting material, and then when that melted material solidifies, you get these burrs. So you have to finish these catheter shafts in order to actually use them, so you don't just, cut and scrape into your patient as you're inserting into them. So the way this is traditionally done is with a chemical finishing process. So you use a chemical to sort of like melt away and polish your material, your workpiece. So one advantage of this process is that chemical machining and chemical finishing processes are very good for mass production. You can do large quantities all at once. You just soak them in a bath, you take them out, you dry them out, and you're good to go. But one major disadvantage is that these are harsh chemicals with electrolytes and chemicals, and these can have harmful effects both on the environment when we dispose of these baths when we're done with them, and they also have the potential to have maybe harmful effects on humans. The fumes from it, not only just on the workers, but if any of that lingers, we don't want any sort of traces of those chemicals on the product when they get used on patients. So there's a strong desire to try to replace this process with something that doesn't use these harsh chemicals and is a little more environmentally friendly. So take a wild guess what process we can use instead. MAF. Isn't there another picture? There we go. So here we have examples of two different catheters and flexible shafts being used with MAF. You can see the one on the left and the one on the right. The one on the left is a lot more stiff, so there's fewer slits, which you can see on the zoomed in cross section. So you see there's just that one slit in that one little area, whereas the other one has a bunch of little tiny slits in it, which is allowing it to be super flexible. And the way you would do this is the same way you've seen before. You have your magnets on your two sort of quadrants, your top and your right quadrants, and then we're going to rotate our workpiece. And as a result, I missed something, so sorry about that. Let me back things up a little bit. So in this case, we're not just using magnetic particles. We're going to use like an iron brush. So we're going to use like an actual piece of like steel with your magnetic particles and your abrasive. So that steel is going to help guide our field lines a little bit further. So you can see here, this little like gray tube here, that's our carbon steel. I think it's carbon steel. In this case, it might be stainless steel. I'm not sure. But we have an actual rod with our magnetic abrasives. Now you can see here, magnetic rod and a magnetic abrasive, and then we're going to use that magnet to move our rod and our abrasive back and forth inside of our workpiece. And we're also going to rotate our workpiece, so we're not just machining the bottom surface, we're also going to rotate so we can get the entire internal surface grinded away. Okay, so now we're going to talk about magnetic tool behavior using these rods to sort of guide your magnetic field lines. So the first case is the case that we're using a carbon steel rod. So carbon steel, you should hopefully be aware, is very ferromagnetic. So it's ferromagnetic throughout the entire tube. So what's going to happen is, if you look at this case here in the middle here, you have your field lines from north to south, but they're going to flow into and within your carbon steel tool. So you have field lines going up into your steel tube, not steel tube, your steel rod, go through it, and then out through into your south pole. But again, because your carbon steel is ferromagnetic throughout the entire rod, what happens when you move your magnet? What's going to happen is, because your entire part is ferromagnetic, and ferromagnetic materials don't necessarily have an inherent polarity. So if you put like a north pole magnet up to a carbon steel, the carbon steel is going to act like a south pole magnet. if you move a south pole magnet to your carbon steel, it's going to act like a north pole magnet, right? And what's going to happen is, so our magnets are essentially attracted to the entire length of this workpiece. So what's going to happen is, if we move this north magnet along the tube, or not along the tube, along your rod's not going to move, because your magnet is just as attracted to this section of your tube as it is to this section, as it is to this section, as it is to this section. So the only point where your rod's going to actually start to move with your magnets is once you get past it. Because once you get to this point here, your south pole is going to, as you move this, your south pole is going to drag your magnet. So there's a lot more lag in your motion as a result of that. So rather than moving like magnetic tool magnets moving like this, it'll move like this. There's a big lag, and you have less motion as a result of that. We don't really want that. So let's talk about a metastable stainless steel tool. So a metastable stainless steel tool is partially magnetic. So you have your field is concentrated on the ends of your tube, essentially. So what happens there is you'll get a little bit better of a motion as a result of that, but still not perfect. There's still a little bit of a wiggle. So rather than your part starting to move, all the way at the end of the rod, it'll start to sort of move at like the halfway point, because it's still attracted to this end. So once you reach the end of that like magnetic region, that's when it'll start to move. So it'll work a little bit better. Again, in this case, you see your abrasive particles are moving, but your rod isn't. One process that we'll do to try to improve this a little further is that you could heat treat your stainless steel to change the phase of your stainless steel from FCC to BCC. So you guys are now in a graduate level. Essentially, this class sort of is a follow-up to production engineering. So hopefully you guys are familiar with your steel diagrams, what's it called, the iron carbide diagrams, your phase diagrams. So FCC, BCC, austenite, ferrite, your different phases and what sort of crystal structures you get with your steels. So depending on your crystal structure, that will influence whether or not your steel is ferromagnetic or not. So if we can heat treat regions of our stainless steel, we can transition from FCC to BCC. Anyone here want to take a guess as to which one of the two is ferromagnetic and which one is not? I feel like I kind of gave the answer away already, but anyone want to take a shot? It's Friday, I know. No one wants to do anything on Friday. That's fine. So FCC is not ferromagnetic and BCC is. And the way I try and do that is that the F, it can be a little confusing because you think F ferromagnetic, but F is not ferromagnetic. That's kind of what I do to try to remember that. If we can heat treat specific regions, we can basically make magnetic and non-magnetic regions of our tool piece, and you'll see that as a result, your abrasives and your ferromagnetic particles will adhere to certain regions of your tool. So as a result, you get better grip. So we'll have this entire region, basically, this localized region here and here, two magnetic spikes here, two magnetic spikes here. And as a result of those two magnetic regions here, your rod is going to be attracted to your magnet at those specific regions. So as you move your magnet, the magnet should move along with it in phase. So just a neat little application of heat treating this stainless steel rod to get a better tool motion. All right, this here is just a diagram sort of showing you like the phase changes. So here we have a spike here at an FCC region. Well, actually, no, I think the spike here is a BCC region, if I'm reading this correctly. Yeah. Here it's FCC, FCC, and then you have a little spike here, BCC, FCC, FCC, and then I think you have a spike at a BCC. Yeah, this diagram, all in all, isn't super important. You'll get a better description if you want to read this paper here. Oh, let me go back. In case you aren't aware, Yamaguchi H is Dr. Greenslit. Yamaguchi's her maiden name. So if you see a paper by Hitomi Yamaguchi, that's Hitomi Greenslit. So this is one of her past papers that she had published in 2011. So it's from her past work herself. Yeah, just me bragging a little bit there. This is just a diagram showing you the different regions of FCC and BCC in this deal. All right, now we're going back to that catheter shaft application with the flexible tubes. So this is before and after MAF using that heat-treated stainless steel tool that we talked about. So you can see before, very dull, lots of rough edges you can see. And then after the process, you have a much better, smoother, shinier surface as a result of that. And one that, ideally would no longer cut into your patients and harm them. So that's always good. Okay. I think this will be, let me double check ahead. Yeah, I think this is probably going to be our last slide for the day. We're starting to run a little low on time anyway, it seems. So last application of a static magnetic field. So once again, we have that same sort of magnet configuration where we have 2 north poles, 2 south poles. Field lines are once again the same from north to south. In this application, we're going to rotate our magnets. And then we can either we can move this rotating magnetic field and the abrasives along our tube, or we can move the tube through the magnetic field. Is this a video? It's not. I wish it were. So what's going to happen is, because of this configuration, we can move using a robot arm. We can use this rotating part, guide it along the bend, and even bend curved surfaces. So you can polish and finish inside, like bent geometries and bent tubes as well. So you don't just have to do a straight back and forth straight tube. You can do bends as well. So here we have actual results of 2 different bent tubes. The second one on the bottom is a much tighter bend radius than the one on the top, but we're able to get, as you can see, very, very, very shiny surfaces. You can see those edge regions were left unfinished just for comparison. So this is before MAF, after MAF, before, after. And we have roughness values to show you exactly and quantitatively how much of a difference it made. So we went from 2.68 microns RA to 0.03. So that's a significant difference. What is that, like 1% roughly of what it was originally? And then on the tighter bend radius, not as good as the smaller bend radius, but still very, very close. So we had 0.06 microns RA from what was originally a 2.54 RA. So the point of this application is to show that you don't just have to work with straight workpieces. You can work with some complex geometries. So it allows you to be very flexible with your workpieces. Like I said before, you can work with both ferromagnetic and non-ferromagnetic workpieces. The ferromagnetic workpieces might need a little more thought, maybe perhaps a stronger magnetic field as well, but it is possible with both. And once again, just to summarize, you can also use this with a ferromagnetic abrasive or a non-magnetic abrasive mixed in with a magnetic abrasive. So it's a very flexible tool. Neat little process. I think we're going to end here. This is probably a good stopping point. Dr. Greenslit should be back on Monday to pick up where I leave off, and she'll go over the more fluids based. So we talked mostly, what we talked about today's lecture was your solid powder abrasive. So you have a mixture of 2 different powders and it's all solid. What she's going to probably talk about on Monday is, okay, what happens if we use like a magnetorheological fluid? So you have an actual slurry, so it's whether that's a water-based or an oil-based fluid mixed in with magnetic particles and an abrasive. So you have as a result of that, we're doing like you have more of a flow and perhaps a finer finish. Like I said before, we're going from large particles to smaller particles, and as you go to smaller particles, you get finer finishes, less material removal, but a better surface finish and a finer material removal. All right, I'm going to wrap that up for today. If you guys have any further questions, feel free to come by after class and ask. Dr. Greenslit will be back on Monday, and remember, homework grades will be posted in a matter of a few minutes, within the hour. You have 1 week to dispute any of those grades. Okay? Have a good day, everyone. Have a good weekend.